Hi, welcome back to my class in differential equation. And last lesson we took up the meaning of differential equations, and we classify differential equations as ordinary differential equation and partial differential equation. We said that differential equation is an equation that contains a function and its derivatives. And ordinary differential equation is a differential equation that contains ordinary derivatives, which happens when the given function is a function of only one independent variable. On the other hand, partial differential equation is a differential equation that contains partial derivatives of a function of two or more independent variables. For those of you who missed lesson 1 in differential equation, please search for my video R teaches differential equation. And for today, we will take up two other classification of differential equations. Differential equation may be classified according to their order and degree. We start with order of differential equation. The order of a differential equation is the order or differential coefficient of the highest order derivative of the function that appears in the given differential equation. But in determining the order of a differential equation, just look for the highest derivative of the function that occurs in the given differential equation. And the order of that highest derivative or the differential coefficient of that highest derivative is the order of the given differential equation. We consider the following examples. Number 1, x, the second derivative of y with respect to x. The first term is x times the second derivative of y with respect to x, minus 3 times the square of the first derivative of y with respect to x equals 2x times e to the power y. This is an ordinary differential equation because it contains ordinary derivative. The derivative of y with respect to x is the first derivative of y with respect to x. And this differential equation contains the second derivative of y with respect to x. And these two derivatives are ordinary derivatives, and the function y is a function of only one variable, independent variable x. And we said that the order of a differential equation is the order or differential coefficient of the highest derivative that occurs in the given differential equation. In this equation, we have the second derivative of y and the first derivative of y. Hence, the highest derivative that appears in this equation is the second derivative of y, and its differential coefficient or order is 2. The order of the highest derivative, the second derivative that appears in this differential equation is 2. Therefore, this differential equation is said to be a differential equation of order 2. Or we say that this differential equation is a second order differential equation. So example 1 has an order of 2. When we say that the differential equation in number 1 is a differential equation of order 2. It is a second order differential equation. Consider number 2. We have 3 times the square of y double prime. Y double prime indicates the second derivative of y with respect to x. The second term is negative xy times y prime. Y prime indicates the first derivative of y with respect to x is equal to tangent x times y triple prime y triple prime indicates the third derivative of y with respect to x plus y e to the x. This differential equation in number 2 is also an ordinary differential equation because y is a function of only one independent variable, x. Y prime, y double prime, y triple prime are ordinary derivatives of y with respect to x. In this given differential equation, the highest derivative is the third derivative of y with respect to x. So the differential coefficient or order of the highest derivative that appears in this equation is 3. Therefore, this differential equation is said to be a third order differential equation. Or we say that the order of this differential equation is 3. We write order 3. The differential equation given in example 2 has order 3 because the highest derivative that appears in this equation is the third derivative of y with respect to x, or the order or differential coefficient of the highest derivative of y that appears in this equation is 3. Thus, this differential equation in number 2 has order 3. Consider number 3. We have y prime. Y prime denotes the first derivative of y with respect to x plus py. Y is the given function. It is a function of only one variable x equals q. Q at the right side of the equation and p at the coefficient of y can be a constant, or can be 0, or they can be functions of x. This is actually the general form of a linear equation in y. The exponent of y is 1, and the exponent of the first derivative of y is 1. So this is a differential equation, linear differential equation in y. There is only one derivative that appears in this equation, and it is the first derivative of y, denoted by y prime. So the highest derivative that occurs in this differential equation is 1, and the order or differential coefficient of the highest derivative that appears in this equation, y prime, is 1. Therefore, this differential equation is a differential equation of order 1. The differential equation in example 3 is a differential equation of order 1. Or we say that this linear differential equation in y is a first order linear differential equation. We also say that this differential equation in number 3 is a first order linear ordinary differential equation. This differential equation can be written more specifically as dy dx. Y prime denotes the derivative of y with respect to x. Hence, y prime can be written as dy dx. And we specify that the coefficient p of y and the right-hand side of the equation q are functions of x, but they may be constants or functions of x. This is again a differential equation of order 1, and it is a linear equation, and it is an ordinary differential equation. Hence, this differential equation is a first order linear ordinary differential equation. A more specific example of a linear differential equation, linear in variable y, is this differential equation in number 4. In number 4, we have dy dx minus quantity x plus 1 multiplied by y equals 2x. by comparing this differential equation in number 4 with the general form of linear equation in y. You can see that q of x equals to x, and the coefficient p of x of y is negative x plus 1. This is a linear differential equation because the exponent of y, the dependent variable y, is 1, and the exponent of the first derivative of y with respect to x is also 1. And the highest, this is a linear differential equation in y. And the highest derivative that occurs in this equation is the first derivative of y with respect to x. Thus, the order or differential coefficient of the highest derivative in this equation is 1. So this equation is a differential equation of order 1, and it is a linear differential equation in y. And because it contains ordinary derivative of y with respect to x, this is an ordinary differential equation. This is a first order linear ordinary differential equation. We write the order of this differential equation. The differential equation in example 4 has order 1. In number 5, we have an example of a partial differential equation. We have the partial derivative of y with respect to x. We have the third partial derivative of y with respect to z. And the second partial derivative of y with respect to u. And by inspection of this given differential equation, we say that y is a function of 3 independent variables. And those are x, z, and u. And by inspection also of this given differential equation, the highest derivative of y is given by the third derivative of y with respect to z. Thus, the order or the differential coefficient of the highest derivative of y in this given differential equation is 3. Therefore, this partial differential equation has order 3. Again, in determining the order of a given differential equation, whether it is ordinary differential equation or partial differential equation, you look for the order or differential coefficient of the highest derivative of the function that occurs in the given differential equation. And the order of the highest derivative of the function or the differential coefficient of the highest order derivative in the given differential equation is the order of the given differential equation. We will now take the difference between linear and non-linear differential equation. Although we have already one example of a linear differential equation in y. This is the linear differential equation in y of order 1, and it is an ordinary differential linear equation. Before we differentiate a linear differential equation from a non-linear differential equation, first we classify differential equation according to its degree, or we take the degree of a differential equation. The degree of a differential equation is given by or is represented by the power or the exponent of the highest derivative that appears in the given differential equation. Again, the degree of a differential equation is given by or is represented by the highest exponent or the highest power of the highest order derivative that appears in the given differential equation. And not all differential equations have degrees. Only those differential equations that are polynomial equation in the derivatives of y, the derivatives of the function involved in the given differential equation, can have a degree. Again, only those differential equations that can be written as a polynomial equation in the derivatives of the function involved in the given differential equation can have degrees. We take some examples. Number 1, we have x times the second derivative of y with respect to x. Minus 3 times the square of the first derivative of y with respect to x dy dx equals to x e to the y. Earlier we said that this differential equation is a second order differential equation because the highest derivative that appears in this equation is the second derivative of y with respect to x. So this differential equation is of order 2 because the order of the highest derivative in this differential equation is 2. Now this differential equation can be written as a polynomial equation in the derivative of y, which means that we can arrange the terms of this differential equation according from the highest exponent of the derivative of from the highest exponent of the derivative of a function y. In general, a polynomial expression p of x is of this form. If p of x is a polynomial expression, then it can be written in this form: a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub n minus 2 multiplied by x to the n minus 2 plus up to plus a sub 2 x squared plus a1 x plus a sub 0. The last term is a constant term, a sub 0. You can see that in this expression, polynomial expression, the exponent of x is decreasing, is arranged. The terms are arranged according to decreasing powers of x. In the first term, we started out with the highest exponent of x, n, and it is decreasing by 1 until the exponent of x in the last term is 0. A sub 0 can be written as a sub 0 multiplied by x to the power 0. But by property of exponent, if x is a non-zero base, x to the 0 is 1 multiplied by a sub 0 equals a sub 0. So the last term is a constant term, but it can be written as a sub 0, x sub 0. Again, a polynomial expression in x can be written in this form. It can be written, its terms can be written according to the decreasing exponents or powers of x. And in this polynomial expression, the first term begins with the highest exponent of x, n. And the exponent of x is decreasing until it becomes 0 for the last term. A differential equation that can be written as a polynomial equation in its derivatives can have a degree, such as this one. This differential equation can be written by according to the highest exponent of the derivative of y. So this is a polynomial equation in derivative of y. And the degree of this differential equation is the exponent of the highest derivative that appears in this equation. The highest derivative in this differential equation is 2. And its exponent, this can actually be written as second derivative of y with respect to x to the power 1. Hence, this differential equation of order 2 has degree 1. This differential equation has degree 1 because the exponent of the highest order derivative in this differential equation is 1. But if the exponent is 1, we omit 1 and we simply write this as the second derivative of y with respect to x. And it's understood that without the exponent 1, the exponent of the second derivative is 1. Hence, the degree of this differential equation is degree 1. We say that this differential equation is an ordinary differential equation of order 2 and degree 1. Consider number 2. In number 2, we have 3y triple prime. Y triple prime is the third derivative of y with respect to x minus xy y prime equals tangent of y double prime. So here the trigonometric function tangent is a function of the second derivative of y plus y e to the x. Now this differential equation has order 3 because the highest derivative that occurs in this differential equation is the third derivative. And its order is 3, or the differential coefficient of the highest derivative in this differential equation is 3. Hence, this differential equation has order 3. But the degree of this differential equation is not defined because this term at the right hand side of the given differential equation is not a polynomial in the derivative of y. This equation contains a trigonometric function tangent of the derivative of y. And this cannot be written as a decreasing exponent of the derivative of y. Hence, the degree for the second differential equation is not defined. We say that the degree of the differential equation in example 2 is not defined. Number 3 we said is the general form of linear equation, linear differential equation in y, linear in y. And we also said that this linear differential equation is a first order linear differential equation because the highest derivative that appears in the linear differential equation is 1. And the exponent of the highest derivative that appears in linear equation is 1. So this first order, this ordinary linear differential equation of order 1 has degree 1. Again, this linear differential equation in y has degree 1 because the exponent or the power of the highest derivative in the linear differential equation is 1. The highest derivative in a linear differential equation has order 1, and its exponent of the highest derivative is 1. Therefore, this is a ordinary first order linear differential equation of degree 1. Consider number 4. We also said earlier that number 4 is an example, a specific example of linear differential equation in y. Linear because the exponent of y is 1, and the exponent of the highest derivative that appears in this equation is also 1. dy dx is the same as dy dx to the power 1. In a linear differential equation such as this linear differential equation in y, the highest derivative that appears in the linear differential equation is the first derivative. And the order of the first derivative is 1, so the linear differential equation has order 1. And in a linear differential equation, the exponent of the highest derivative that appears in the linear equation is 1. So this ordinary first order linear differential equation has degree 1 because 1 is the exponent of the highest derivative in a linear differential equation. And in a linear differential equation, the highest derivative that you will see is the first derivative or derivative of order 1. So this example 4 is a first order differential equation of degree 1. Now consider number 5. Number 5 is a partial differential equation, and we said that its order is 3 because the highest derivative of y that appears in the given differential equation is 3. And the exponent of this, or the power of this highest order derivative that appears in this differential equation is 1. Hence, this partial differential equation has order 3 and degree 1. Degree 1. Again, the order of a differential equation is given by the order or differential coefficient of the highest order derivative of the function that appears in the given differential equation. And the degree of a differential equation is represented by or is given by the exponent or the power of the highest order derivative of a function that occurs in the differential equation. And not every differential equation has a degree. Only those differential equations that can be written as a polynomial equation in the derivative of the function, in derivatives of the function involved in the given differential equation can have a degree. We take two more examples of finding the order and degree of a given differential equation. Consider the following examples. In the first example, we have the difference of the second derivative of y with respect to t, and 3t times the first derivative of y with respect to t raised to the power 4. So obviously our function y is a function of only one independent variable t, plus the cube of the third derivative of y with respect to t minus 5t equals 0. The order of this differential equation is given by the order or differential coefficient of the highest order derivative that appears in this differential equation. And we have the derivatives of y that appears in this equation are the second derivative of y, first derivative of y, and third derivative of y. And the order of the highest derivative is 3. The highest derivative that appears in this differential equation is the third derivative of y, given by d cube y over dt cube. Thus, the order of the highest derivative that appears in this differential equation is 3. Therefore, this differential equation is a third order differential equation, or this is a differential equation of order 3. Now, the degree of this ordinary third order ordinary differential equation, its degree is given by the exponent of the highest derivative. This is the highest derivative, the third derivative of y with respect to t, and its exponent is 3. Therefore, this ordinary third order differential equation has degree 3. Consider this second differential equation. We have x cubed times the fourth derivative of y minus 5x squared times the third derivative of y plus 2x times e to the power y prime. This is an exponential function. E is raised to the derivative of y equals cosine. Cosine is a trigonometric function, and the angle is, the cosine is a function of 2x times the derivative of y. The order of this differential equation is given by the order of the highest order derivative that appears in this equation. The highest derivative that appears in this differential equation is the fourth derivative of y. Hence, the order or differential coefficient of the highest derivative in this differential equation is 4. Therefore, this differential equation is a differential equation of order 4. This differential equation in example 2 has order 4. But this second differential equation cannot be written as a polynomial equation in derivatives of the function y, because there are two terms that are not powers of the derivative of y. We have the exponential function, and we have a trigonometric function cosine. Therefore, the degree of this differential equation is not defined. The degree of the second differential equation is not defined. And the degree of this differential equation is not defined because we cannot write the terms of this differential equation as a polynomial equation. That is, we cannot write the terms according to the decreasing powers of the derivatives of y. Hence, the degree of this second differential equation, because of this cosine and this exponential function, is not defined. We now state the conditions that must be satisfied by a linear differential equations. These are actually the criteria for determining whether the given differential equation is a linear differential equation or nonlinear. If one or more of these conditions are not satisfied, then the given differential equation is said to be a nonlinear differential equation. These are some of the important notes to remember when determining whether the given differential equation is a linear differential equation. In the following criteria, we take the function y as a function of only one independent variable. Number 1, in determining whether a differential equation is linear or nonlinear, only the function y and its derivatives are used. That is, we examine each term of the given differential equation and we consider only those terms or factors in the terms of the given differential equation that contain y and its derivatives. We do not consider those functions of x or the functions of the independent variable x. Only y and its derivatives will affect the process of determining whether the given differential equation is linear or nonlinear. If the differential equation is a linear differential equation, no product of y and its derivatives appears in the given differential equation. Hence, each term of the given differential equation, if it is a linear differential equation, contains y, a term with y, and multiplied by any of its derivatives. Number 3, neither y or its derivatives occur to any power other than the first power. That means if you have a differential equation containing a term with y raised to an exponent higher than 1, then the given differential equation is definitely nonlinear. Or if you have a differential equation that contains with terms containing derivatives of y raised to an exponent other than 1, say 2, 3, or 4, then the given differential equation is non-linear. And number 4, neither y or its derivatives are inside another function. That means if you have a trigonometric function, say cotangent of a derivative of y, then the given differential equation is definitely not linear. Or if you have a term containing the root of a derivative of y, then the differential equation is non-linear. Or if you have a term of a differential equation containing an exponential function, say e to the power to an exponent, and the exponent is a derivative of y or y, then the given differential equation is not linear. Again, in determining whether the given differential equation is linear or non-linear, we only consider the y, the dependent variable y, and any of its derivatives. And in a linear differential equation, the exponent of y and any of its derivatives is 1. And in a linear differential equation, in any terms of the given differential equation that is linear, there is no product of y and any of its derivatives. And lastly, a linear differential equation does not contain the derivative of y inside a function, such as cosine of the derivative of y, or the root of a derivative of the function, or an exponential function with the derivative of y as the exponent. We will now take examples of differential equations, and we will determine whether each differential equation is linear or non-linear differential equation. Consider the following differential equations. We will now determine whether each differential equation is a linear or non-linear differential equation. Number 1, we have dy dx equals x over y plus 1. At the left-hand side of the equation, we have the first derivative of y with respect to x, and its exponent is 1, or the power of dy dx is 1. At the right-hand side, in the denominator of the first term, we have y with a power of 1. But suppose we multiply both sides of the equation by y. We multiply the left-hand side by y. We have dy dx multiplied by y, and multiply each term of the right-hand side by y. Xy multiplied by y, y will cancel out, and you get x plus multiply 1 by y, we get plus y. At the right-hand side of the equation, the exponent of y, the dependent variable y, is 1. At the left-hand side of the equation, again, in determining whether a differential equation is linear, we only consider y and any of its derivatives. At the left-hand side, we have the first derivative of y, dy dx, but with an exponent of 1, and we have y as one of the factors at the left-hand side of the equation, and the power of y is 1. But we said earlier that a differential equation that is linear does not contain the dependent variable y and does not contain a product of the dependent variable y and any of its derivatives. But here at the left-hand side of this differential equation, we have the product of the dependent variable y and its derivative dy dx. Hence, this differential equation in number 1 is non-linear. Again, the differential equation in number 1 is nonlinear because if we multiply both sides of the equation by y, we obtain a product of y and its derivative. And we said that a linear differential equation does not contain any products of the dependent variable and any of its derivative. Consider number 2, we have x squared times the second derivative of y with respect to x minus dy dx, the first derivative of y with respect to x, plus y equals 0. Now we consider y and any of its derivatives in each term of the given differential equation. Here we have the second derivative of y with respect to x and its power is 1. In the second term, we have the derivative of y, first derivative of y with respect to x, and its power is also 1. And similarly, in the last term, we have y, and its power is 1. Thus, we see that the dependent variable y and its derivatives have all the same power of 1. And in a linear differential equation, the dependent variable y and any of its derivatives must be raised to a power not more than 1. Therefore, this differential equation is linear differential equation. Consider number 3, we have x times y prime. Y prime is the first derivative of y with respect to x minus quantity x plus 1 multiplied by the square of the second derivative of y minus y equals x. In determining whether a differential equation is linear or nonlinear, we consider y the dependent variable and any of its derivatives in the given differential equation. In the first term, the exponent of y prime is 1. In the second term, the exponent of the second derivative of y double prime is 2. In the last term, at the left-hand side of this differential equation, the exponent of y is 1. And this differential equation is not linear because it contains the second derivative of y double prime, raised to an exponent that is more than 1, 2. Hence, this differential equation is nonlinear. Nonlinear differential equation. A linear differential equation does not contain the dependent variable y or any of its derivative raised to an exponent that is more than 1. But this differential equation in number 3 contains a second derivative of y raised to an exponent 2 which is more than 1. Thus, this differential equation is not linear. We say that it is a nonlinear differential equation. Consider number 4. We have x y double prime. Y double prime is the second derivative of y with respect to x minus 5y prime equals ln of x minus 1. Again, in determining whether a differential equation is linear, consider only y, the dependent variable, and any of its derivatives in the terms of the given differential equation. In the first term, we have the second derivative of y and its power is 1. So the first term is good. The second term is negative 5y prime. It contains the first derivative of y and its exponent power is 1. So the second term is good. And the right hand side of the equation is okay because it's only a function of x. Therefore, this differential equation in number 4 is a linear differential equation. For instance, at the right-hand side of the equation, instead of ln of x minus 1, we have ln of y minus 1. Now, the dependent variable y is now inside a function, the natural logarithmic function, and this makes this differential equation a nonlinear differential equation. We said earlier that a nonlinear differential equation does not contain y or any of its derivatives inside another function. But in this case, y is inside the natural logarithmic function. So this makes this differential equation a nonlinear differential equation. But originally this is x. Hence, this differential equation is a linear differential equation. For the last example, consider y minus x equals xy y prime plus 1. The last term at the right-hand side is a constant term. At the left-hand side, the power of y is 1. But the first term in the right-hand side of the equation, we have a product of the dependent variable y and its first derivative y prime. And we said that a linear differential equation does not contain any products of the dependent variable and any of its derivatives. But in the first term at the right-hand side of this differential equation, we have a product of y and its first derivative y prime. So this term makes this differential equation a nonlinear differential equation. Again, if a differential equation is not linear, then the differential equation is a nonlinear differential equation. And in determining whether a differential equation is a linear differential equation, we only consider the dependent variable and any of its derivatives that appear in the given differential equation. In the given differential equation that is linear, no products. We do not find any products of the dependent variable and any of its derivatives in any terms of the given linear differential equation. And the power or the exponent of the dependent variable or any of its derivatives in a linear differential equation is 1. And the dependent variable or any of its derivative cannot be found inside another function in a linear differential equation. In the next lesson, we will take up solution of a differential equation, and they are classified as general solution or particular solution depending on the information given in the problem involving differential equation. If you have questions about the lesson today on order and degree of differential equation or about linear and nonlinear differential equation, you ask your questions in the comments below. But do not forget to subscribe to my YouTube channel, Art Kalison. And thank you for joining me in the class today.